Now it's we move to the next excellent step. We have invited our participants to give a short description of their system, especially highlight how they win the challenge, how they obtain such a big improvement. Actually, the improvement is quite significant. Before the ER is about 10%, but right now it's below. I think it's below 5. So the improvement is quite impressive. Okay, let me invite the first technical report. It's from team 082. It's from Shanghai Jiaotong University. It's let's see. Oh, Chen Zhengyang. I think that the speaker is the presenter is Zhengyang, right?
Yeah, I'm here.
Okay. I heard you. Okay, I'll give it to you. 1 second. Stop my share.
Can you see the slide?
Right. Yes.
Okay. Hello, everyone. I'm Zhengyang Chen. Here I represent the SG2 Excellence Lab System for CNSRC 2022. And the team members are Zhengyang Chen, Bei Liu, Bing Han, Leying Zhang, and Yanmin Chen. In this challenge, we submit our results into 2 tasks. In the speaker verification task, we achieved 0.29 millisecond and 4.9 equal error rate. In the speaker retrieval task, we achieved 0.46 mean average precision. In the following slides, I will give a detailed introduction about our system in this challenge. For the 3 tracks, we follow the same data usage setup. In the experiments, we use the SynSalab 2 data site and the SynSalab 1 depth site as a training site. We also noticed that there are so many very short utterances in the speaker training site. We combine the short utterances from the same speaker and the same genre to make each utterance longer than 5 seconds. At the table shown, the speaker and utterance number after and before the combination. It should be noted that we only do this combination on the training data. The evaluation set remains the same. To improve the robustness of our system, we applied 3 different augmentation methods. The first one is the additive noise from Musen data site, and the second one is the reverberation from IR data site. Besides, we also applied the speed perturbation by speeding up or slow down the utterance with ratio 1.1 and 0.9. Because the speech perturbation changed the pitch of the audio, we will consider the utterance from new speaker. For each utterance, we extract 80-dimensional F-bank feature, and no VAD is applied in our experiment. Last few years, we have seen lots of different architectures designed for speaker verification system, such as TDM-based model, ResNet-based model, transformer-based model, and the models which take raw audio as input. In our experiment, we found that the complex and large models always have serious overfitting problem. Although data mutation can solve this problem to some extent, we still cannot fully solve this problem. Interestingly, we found the R-vector-based model doesn't seem to have this problem, and we will mainly use R-vector in our experiments. The configuration of R-vector is shown in the left table. Compared with the ResNet 34 in the original ResNet paper, the R-vector replaced the first convolutional layer with small kernels and abandoned the max pooling layer to make it more suitable for acoustic feature input. Besides, the channel number is also cut in half from 64 to 32 to reduce the model parameters. After several residual blocks, a statistical pooling layer is used to map the variable length input to a fixed dimensional representation. Finally, a linear layer is used to get the speaker embedding. In our experiment, we also make the R vector deeper to enhance its modeling ability. The residual block is changed to bottleneck chip. We tried 3 different configurations for the deep R vector. The ResNet 152, the ResNet 221, the ResNet 293. In our experiment, we split the training to 2 stages. In the stage 1, we use the additive angular margin loss as the training objective, and the set the margin to 0.2. We randomly sample a 2-second segment from each utterance to construct the training batch. In the stage 2, we do the larger margin fine-tuning by enlarging the margin to 0.5 and using longer segment. Besides, we also abandon the speech perturbation in this stage to make data more matched with the real data. In the scoring stage, cosine similarity plus adaptive score normalization is used. Besides, we also noticed that there are multiple utterances for each enrollment speaker. We tried 3 different ways to leverage multiple utterances for enrollment speaker. The first method is the utterance concat. Here, we concatenate the utterances belong to the same speaker to one long utterance. The second one is the embedding average. Here, we average the embeddings of the enrollment utterances from the same speaker to one embedding. And the third one is the score average. Here, we average the score between one test utterance and the multiple enrollment utterances from the same speaker. In our experiment, we first tested the 3 different strategies to leverage the multiple utterances from the same enrollment speaker. And we found the embedding average achieved the best result. Besides, from this table, we can also see that the AS norm can bring large performance improvement. The speed perturbation augmentation has become very popular in recent speaker-related challenges, and we test its effect here. We found that the speed perturb can bring consistent improvement on the mean DCF and the equal error rate evaluation metric. And the improvement on the equal error rate is significant. Here we list all the results which are used for summation. Here the DF ResNet is another work published in Interspeech 2022, which aims to design a rule to make ResNet deeper and keeps the model set smaller at the same time. From the results, we found the large margin fine-tuning can consistently improve the performance. Another interesting finding is that the mean DCF metric and the equal error rate metric are not always consistent. Compared with the ResNet 152, the DF ResNet has worse equal error rate, but much better mean DCF. We also show the false negative rate and the false positive rate when we get the mean DCF value in this table. We can see that the mean DCF is more correlated with the FNR when the FPR is constrained to a very small value. Besides, we fuse all the large margin fine-tuning models according to their performance as our final model. Next, I will introduce some other attempts we have tried. Actually, we have tried some other networks in our experiment, like TDN-based eCover TDN. However, compared with ResNet, it performed much worse, and we didn't use it in our summation. Apart from the model structure, we also tried to leverage the run information in the experiment. The first attempt is to use the adversarial training to remove the run information in the embedding. Here, we implement this by adding a gradient reversal layer before the genre classification height. However, we didn't see a very obvious improvement. The second attempt is to leverage the genre information in the score collaboration stage. As the equation in the bottom shows, S is the original score, and Q is some additional factors which are used to calibrate the score. Here, we use the genre similarity between the enroll and the test utterance as the additional factor. To get the genre similarity, we trained a genre classification model based on eCappa TDN, and then extract the genre embeddings. We can get the genre similarity using the quotient score between the enroll and the test genre embeddings. However, in this experiment, we found that the score collaboration training objective is more related with the equal error rate evaluation metric. After collaboration, the equal error rate is improved, but the mean DCF value degrade. Besides, for the retrieval task, we didn't take too much time and directly submit the score of ResNet 221. Finally, thanks for the efforts of our team in this challenge. That's all.
Thank you, Zhengyang. Very nice report, and especially you presented some field experience, and I think that's very interesting for us. Any questions from our audience? And if you have some questions, you can post them on the chatting box, and then we'll collect them and forward them to the presenter. Okay, I have a question, Zhengyang.
Okay.
You said that when you use the genre information,
Yeah.
you didn't get any improvement.
Actually, I got the improvement on the equal error rate evaluation metric, but the mean DCF degrade. Yeah.
Okay, but how about the and also training? It looks like nothing was obtained.
Oh, I think the genre classification number is too many here. The adversarial training will add a gradient reversal layer here, and when the classification number is big, the training can be very unstable. I think this may be the reason. Yeah.
Okay.
Because the adversarial training is a common method in the domain adaptation. In that scenario, the classification number is true, so the task is easier. Yeah.
Okay. Right. Okay. Next question is that you said that you train the system with two phases. In the first phase, you use the speed perturbation and short utterances, and in the second phase, you didn't use speed perturbation and use a longer utterances. What was the consideration?
In the same stage, we want to make the utterance, no matter the length or the audio condition. I want to make them more similar to the real condition. So I remove the speed perturbation and make the training segment longer to make it more similar. Yeah.
Match the test condition. Okay. Good, nice. Congratulations again to the brilliant results, and hopefully you can continue joining us to the next challenge.
Oh, thanks.
Okay, thank you very much.